All right, how's it going, guys? I'll be doing the fluids final review right here. Sorry this is taking a little while to upload. I've been busy with my own stuff, but yeah, it's Justin back doing the review. But you guys should have plenty of time to study, so don't worry about it. So I'm just gonna jump right into it. Once again, the actual PDF should be posted on Canvas along with this video. The link to this video, obviously, this will be on my YouTube. But anyway, all right, so let's get into it. So the first one. And, again, like the last review I did, I'll just write like a brief sentence on it. Just have the PDF pulled up if you want to look along with it. But anyway, so for problem one, we've got the tank in this figure is filled with water, and this gate AC is 3 meters long. It's hinged about A, and it's being held in place by a cable attached to this big spherical ball. And then we also have another gate BC hinged at B, and it's held in place by butting up against gate AC at point C. Note that the cable is attached only to gate AC, not to BC. The depth D, which I did not draw, D is right here. That's the depth right there. That's 2 meters. Gate AC is 2 meters wide, and gate BC is 3 meters wide. So for part A, it asks us to find the radius of the sphere to hold the gate in place, right? So not too bad. So we know the force on gate AC right here is just, the water density times gravity times the volume of water above it. So I'll say, FAC equals rho G of water times V. Right, and this just equals, we're using 1,000 for water. I think the T uses probably like 998 or something. It's close enough. Obviously, we're in meters and stuff, so 9.81 meters per second times, we're just focused on the part that's touching gate AC, so we said it's 3 meters long, so 3 times 2 meters wide, times the volume of the water above it, so another 2 meters from the depth, right? And so this force should be about, let's see, I did 117720 newtons, right? So let's put a little dotted box around that. So that's just the force on that gate right there. And now let's draw a little free body diagram. We'll draw a little free body diagram like right here, of gate AC. Here's gate A, point A, point C. And then this ball is applying some tension force, right? It's coming up like that. And then obviously you have the force of the water. And this distance here is L, and L over 2. Right, so for this tension force is also pretty easy. It's just the weight of the sphere down minus the buoyant force, right? So we can say T equals FB, or I guess W minus FB. W ball minus buoyant force, right? And so this, if you want to math it out, because the buoyant force is just like the volume of water that the ball is displacing, right? So you can just as easily say that it's 4/3 pi r cubed, which is the volume which is the volume of the ball, right, times gravity, times the density of the ball, minus the density of water. Right, and this is 8,000, this is 1,000, and then we're solving for r cubed, right? So go plug everything in. So let's do our force balance equation, right? Let's take moments about point A. Equals 0, and obviously these are pointing in opposite directions, so I'm just going to set them equal to each other right away. So to FAC, which we already know, times L over 2 equals this 4/3 pi r cubed times G times rho B minus rho W times just L, right? It's just the full thing. Okay, you know all these numbers. The only thing you don't know is the radius, which is what we're solving for. Just still plug everything in, solve for, take that cube root of it, right? And we're getting R should be about 0.589 meters, right? And there's part A done. Pretty easy. That one's not too bad. Okay, and then for part B, we want to know, what is the force exerted by BC on AC? And obviously, we're not talking about friction at all. So again, BC, for the force that is actually touching BC and like forcing it into the other gate, that's just the force of the water, right? And so we know, I'll say F, the force of the water. Let's see, how should I want to do this? I'll just call it F water on BC, right? This is just the rho G times height of the centroid times the area of the gate, right? Rho water. And so this is 1,000 times 9.81 times, all right, so BC is 1.5 meters long, so the centroid is right in the middle, 0.75 plus 2, so 2.75 times the area of the gate, which is 1.5 times 3. And so this force should be, I have it written somewhere, 121.398 kilonewtons. All right, that's cool and all, but we don't know where that force is acting yet, so we need to do that, the ZCP equation thing, right? Where we know ZCP, the center of pressure, the height of the center of pressure, and this equation I'm about to write, it'll spit out how far below the centroid is the center of pressure. And so ZCP is equal to the moment of inertia, I at sets, IYY, whatever you want to call it, times height of the center of pressure times the area of the gate, right? Or height of the centroid, wrong terminology, HC. And so I at sets, we're just talking about rectangles, so this is just 1/12 base height cubed, right? Now I always just do times like 1 over, see, so HC we already said is 2.75 times the area again, which is 1.5 times 3, right? Now putting everything in the base, that's just how wide it is, so that's the 3 meters, and then the height is the 1.5 meters. Still plug everything in. The ZCP, the height of the center of pressure is 0.0682 meters below the centroid. Right, and so now we know all that stuff. So now we can draw another little free body diagram where we have, this is point C up here, and this is point B. We have some resultant force, it's pressing like that, FR. And we have the force of the water, which is below the centroid, right? Let's call that HC. That's about midway point. So this is our FW, which is below it, right? And we want to know, it's hinged at B, so we're taking moments about point B. So let's go. So FW, it'll be FW times, we're going from B, so it'll be L BC over 2. And I'm taking minus 0.06. Right, equal to FR just times the length of the thing. All right, we know all these numbers. Plug everything in, solve for resultant force. You get FR equals about 55.1 kilonewtons. Right, it's not bad. That's just the forces keeping it butted up against there. Pretty easy, not too bad. Okay. Number 2. Let's move on. Number 2 is a little more tricky, but it's fairly straightforward control volume problem. Oh, and this question 1 pertained to outcome 2, right? That's your forces on submerged surface stuff, whatever. Okay, number 2. Number 2 has to do with outcome 3. It's a control volume question. And so it says here, we've got a large tank shown in the figure. It's filled with water to a height of H0, H0. Water exits the 5 centimeter diameter pipe at A and is collected at a tub at B. The tub is 2 meters below the pipe exit. You may assume no viscous losses, right? All right, so I'll also say, I forgot. This is D right here. Say D equals what? 0.05. All right, so A is, all right, so for A, the volume flow rate is Q dot equals 0.028 cubic meters per second. All right, at what height, H0, must the tank be filled to achieve that flow rate if P0 is 50 kPa? All right. And we also know P0 gauge is 50 kPa. Everything that's supposed to air, so this P0 in here is just measured in terms of gauge pressure, which is fine. All right, so first off, we can just take Bernoulli's equation from this point way up here, all right? This point way up here to point A down here. So let's do that. So we've got P0, I'll say, Bernoulli's. From H0 to A. And so we get and we're taking point A as our datum point, so we'll call that 0. And then pressure A is it's supposed to air, so we're taking everything in gauge pressure, so we call that 0 as well. And then it's a really big tank, so we're saying V0 is also 0, right? So essentially this just becomes P0 plus rho G H0 equals 1/2 rho VA squared. Right, where we know VA, velocity at A, is just equal to the volume flow rate divided by the area. So Q dot over A of the pipe, which A is just, D squared over 4 times pi. So plug in those numbers. We get VA equals 14.26 meters per second. And now just go plug everything else in, and solve for H0. Again, we're taking is water, so we're taking density to be 1,000 or 998, whatever the hell you want to use. So let's say plug in, solve for H0. This is the easy part. Anyway, the H0 should be equal to about 5.27 meters. And I'm never going to go through all that much of the algebra for it. I mean, the algebra, you guys can do algebra. The hard part is just knowing the connections and why did we use Bernoulli's equation here? Well, because it's inviscid, incompressible, and everything's along a streamline, so boom, no problem. But yeah, so that's the height that needs to have that volume flow rate. So for part B is a little funky. It says using the control volume shown in the figure, which is right here, this is the CV. Show that the velocity in the horizontal direction remains constant as the water flows from A to B. Hint, there is no force in the x direction acting on the control volume. So, I mean, it wants us to use the whole, the integral forms of conservation of mass and momentum. And I will, but it's just kind of, all right. So the simplified version, right, where we know, I'll say, so how do I want to word it? Say that, show that velocity in x is constant, right? But the way I think about this is more of a ballistic equation type thing, like you remember from physics class, there's really no change in your x velocity as you like throw a ball up in the air, because there's no like wind resistance or anything like that. So that's how I was thinking about it. It's just a pretty straightforward thing. But if you really want to, so the simplified conservation of mass, and I'm already just going to get out of, I'm not going to put the time derivative term in there. Everything's steady. It's fine. Go look at your notes if you're confused about that. So we have 0 equals surface rho v dot n ds, where s is just the area. And so we know what comes in has to come out, right? So we have m dot in equals m dot out. And this is just rho VA in equals rho VA out, right? And the way I think about it is density is constant, area is constant, density is constant, area is constant, so V has to be constant, right? Right, and so this is that V vector. V vector must be constant, but whatever, because this is not, this is a thing, but whatever. So V must be constant, okay? So let's move on to conservation of momentum. Where we have 0, because there's no external forces, so I'm just keeping that at 0. We're not taking pressure into account or anything that cancels each other. Where this V, I'll write this as Vx, because we're doing everything in the x direction. So this is Vx right here, right? And so once again, that I'll say like momentum in has to equal momentum out because there's no external forces, right? I'll say mom in equals mom out, right? And so you get rho v squared a. Technically, it's not v squared. It's like vx times v dot n, but whatever. For simplicity, I'll just write that. Rho that was rho v squared a in and out. And again, density is the same, area is the same, density is the same, area is the same. Obviously, Vx has to be constant. Cool, done there. It's just a conceptual thing. I don't think they would ask you to show you this on an exam, but whatever. Anyway, so for part C, we want to know what the angle is, find theta. At which the stream hits the tub. So again, we can do another Bernoulli's equation from A. I'll call this B up here. Right. So Bernoulli's And totally arbitrarily, we're going to take A to be our datum point. Just like I said, totally arbitrary. You could pick B, whatever. But again, everything's exposed to atmosphere, so we're going to cancel the pressures. We're going to cancel HA. And then VB, we don't know VB quite yet, but we can find it. This is why we're doing this, so we can find VB, right? So we end up getting, to solve for VB, we get 1/2 rho VA squared, which we know VA, so that's great, equals 1/2 rho VB squared plus rho GHB. And we know this distance from A to B right here, that's 2 meters. So HB is -2, whatever. Solve for VB. VB is about 15.57. Right? So we know the velocity to be. So great. Now we can say, let's draw another little image down here, right, of our actual, what's actually happening. So we know that VA, that's just the actual, VA is constant. That's how fast the water is coming out here. And we already proved that the velocity in x direction stays the same. So we can call this VA right there. And then this VB is the velocity vector that's hitting the tank, the tub, right? Let's call that VB. And this is the surface of the tub. We're finding theta here. And this is just basic trigonometry, right? So we can just say cosine theta equals VA over VB. And so theta equals cosine inverse of VA over VB. We get theta equals about 23.7 degrees. Right? Again, pretty easy. Not too bad. Just some trig right there at the end. But I would expect a more integral related one on the final. If you're gonna be banking on anything, I'll just say get your integral equation stuff down. But it's really not all that bad. You'll see. Since you have to do all 5 of the questions on this final, they're all going to be fairly short, I would imagine. We're not going to make you do anything too crazy. But yeah, I would expect, just study up on that. It's not the big deal. All right, moving on to 3. Outcome 3 covers outcomes 1 and 4. It's the one you can double test on. So essentially we have a tow test for the drag on a ship. Drag is 30 meters long, speed is 10 meters per second. For part A, we know that the drag D depends on its velocity, its length, the density of the water or whatever fluid it's going in, and the viscosity, dynamic viscosity of whatever fluid, and gravity. And we want to show that the drag coefficient CD is equal to D over yada yada equals a function of Reynolds number and the Froude number, and the Froude number is that. So for this one, we're going to do this kind of in a clever way. So all we're going to do is we're going to we're going to take D and just isolate it and multiply these two things, this rho V squared L squared over. And so we're going to get D equals times some function of RE and FR, right? And so now we can get this into dimensions. So we're not even going to be picking any parameters or anything like that because it already gives us all the stuff that we really need. So we're going to say this is the force. This is F equals we're going to go the velocity L over T to some power A times some length to some power B times M over L cubed. This is density, some power C times M over LT. It's the viscosity to some power D times L over T squared, which is G. This is acceleration. So now break into linear algebra. And so we know, let's group together all of our m's, okay? All of our m terms. So we have 1, because you have 1 sitting over here, 1 equals z plus d. And because c, there's just one c up there, and then just one and there, blah. And so t, do the same thing for t. 2 equals a plus d plus 2e. And then L, do the same thing for L. It's 1 equals a plus b minus 3c minus d plus e, right? And so from all of these, you can say c equals 1 minus d, a equals 2 minus d minus 2e, and b, it's an e, b equals 2 minus d plus e, right? So from all of this, we know we can say that, we can solve for a couple of these. And so from this, we can say that d equals, let's see, what did we say our density was? Our density was c equals rho to the c times our velocity to the a times our L to the b. And from solving these up here, we can say that c equals 1. We can find that c equals 1. V equals 2, or blah. A equals 2, and B equals 2, right? And then we don't know, from all of this, we don't know what, ooh, actually, this is not the way I want to go about doing this. Hold on. So anyway, yeah, so back up a little bit. That's not how I want to go about doing that. Once you solve for a bunch of these, you can see that, once you linear algebra everything all together, you'll get everything in combinations. You get a couple of these to come out where, you have this c equals 1 minus whatever, right? 1 minus d, and a equals 2 minus yada yada. So this a, this corresponds to the velocity right here, right? So this is where that 2 in the v squared, else, the v squared right there comes in. And then with the length, the 2, that's where that L squared comes in. And then you're putting it, for D, you're putting it in this negative portion right here, right? And the same thing for the L over T, the velocity, and the, what would be the Reynolds number. That's where that negative D comes in. So anyway, just math all this stuff out. So you end up getting D equals rho, because A just equals 1, or our density is c. C is 1. So we get rho v squared L squared times some mu over rho VL to some D, right? Times LG over V squared from that negative portion, the negative 2E, whatever, to some E, right? And so this is the Reynolds number right here. And this we can rewrite as the Froude number, where if you just flip it and take the square root of the bottom, it's all the same, or the square root of the whole thing. You can go V over root GL, because the square root of a dimensionless number is still dimensionless, right? And so from this, we can all say, you can just divide this over, divide the rho V squared L squared over, and say CD equals D, divide that over, times some function of these. We don't know these D's and E's, so we can just say it's some function of, flip that, rho VL over mu is Reynolds number. And then we just said that's the Froude number again. Cool, so that's not, that's kind of a trickier one. I wish they would have picked a better one for that, where you actually have to pick parameters, but whatever. So for part B, we're doing a 1 to 30 scale. One to 30 scale test, right? To estimate the drag on the ship. Assuming rho equals 1,000 kilogram, whatever. And mu equals, right, for both the full scale and model scale. You know that the wave drag is more important than the friction drag for conditions under which ship operates, so you make sure they match the Froude number between the model and the full scale ships. Show that it's then impossible to match the Reynolds numbers for this scale test. What is the ratio of the model scale Reynolds number to the full scale Reynolds number? Okay, so we want to match Froude. So we want to say Vm or root, gravity is obviously the same, equals V prototype, the full scale thing, over root GL prototype, right? And so gravity is the same, so I'm just gonna cancel those. And so we get, simplify some stuff over, divide that over. So we get Vm or Vp equals root Lm over Lf or Lp of the prototype. We already said it's a 1 to 30 scale model, so essentially we get equals 1 over root 30, right? And so that is like the ratio, that is like the Froude number right there. 1 over root 30 is like that whole ratio right there. Okay, and now to match Reynolds numbers, we take the same thing but for Reynolds numbers. So we have rho VL model, it's also model, and again these are the same, I'll cancel those, that's the same. So we get Vm Lm equals Vp Lp, and you can see, so again, if you do the math again, divide the Vm by Vp, and then equals, I'll divide that over Lp over Lm. You can see, since it's again 1 to 30 scale model, this has to equal 30. And so these two things right here obviously cannot match. For the same given circumstance, the two things cannot match, right? So you have to try and match one or the other in this whole situation. And so that's what part C is saying to. Having matched the Froude number, you measure the drag on the model under the proper test conditions to be 8.33 newtons. So what is your estimate for the drag on the full scale ship? All right, so we already matched the Froude number. So we're matching Froude numbers in this whole thing. But so for drag though, so I'll say, let's see. So drag equals 8.33. On the model, right? So drag is 8.33 newtons on the model, right? And so now we can use our CDs, where CD equals D times rho, right? And so we know dm equals 8.33. So we can say right, and densities are the same, let's cancel those. We know dm, we can say the length of the model, we can call that 1, and we can call the length of the prototype, the full thing, we can call that 30. And we also know the speed here. Up here, we know the speed for the whole ship, the full scale ship, is 10 meters per second. So we can go back if we wanted to from. I'm not going to go and do the algebra for it because it's easy, but we know the lengths, right? From the Reynolds number, we know the lengths. We know the length of the prototype is 30. We know the length of the model. We can call that 1. We know the velocity, p, is 10 meters per second, and so we can just solve for Vm. I'm not going to write it down there because it's not that big of a deal. It's literally a one-step algebra equation. But anyway, so match these numbers, right? Solve for d prototype. So we get d prototype. Just multiply all that stuff over, equals dm. Multiply it over v squared p times L squared P over VM squared LM squared, right? So just do all that math. Like I said, I'm not writing this velocity of the model because it's super easy to find. Just go do it yourself. Make sure your numbers match the key. We get D of the full thing is 1369 newtons. Cool. Again, not too bad. Just gotta match all your numbers. Make sure not to mess up any algebra as you go along. Not the worst one in the world. This is probably some that'll probably be on the exam, I would say, in some sort of form like this. I think this was like the exam question I got when I took this class a long time ago. So should be pretty legit. Anyway, moving on to question 4. This is a flow rate minor loss sort of thing. So we've got constant flow rate is produced from a large tank with an unknown height, h. The average velocity is 3 meters per second. The pipe has a length of 1 meter, inner diameter of 2 centimeters, and surface roughness of 0.04 centimeters. The inlet from the pipe to the tank is minor loss coefficient KL inlet of 0.25, and then the outlet, the exit to air, is 1. Minor loss is 1, and yeah, it's discharged to the atmosphere. For water, we're using rho is 1,000, and viscosity, I did not write viscosity. Cool. So for part A, we want to know what is the flow. Is the flow inside the pipe laminar or turbulent? All right. Well, this one's pretty easy. If you don't know how to figure this one out on your own, I would say, maybe go back and look at your notes a little bit, because this should be a free money right here. So we know RE obviously depends on the Reynolds number. RE equals rho VD over mu, right? And this equals 1,000 times the velocity is 3 times the diameter is 2 centimeters times 0.02 over 10 to the negative 3, right? And this equals about 6 times 10 to the negative 4. Obviously, that's bigger than the 2,300 we need to be turbulent. So flow is turbulent. So now we'll be using all of our turbulent equations for everything else coming after this, instead of our whatever everything would be for laminar. So for part B, what depth h must be maintained in the tank in order to sustain this flow rate? Let's see. Right. And so, first off, we know our major losses, right? Is equal to whatever our friction factor is times L over D times V squared over 2G And so for F, I'll say use whatever equation you want. The Holland equation, I see a lot of people use. I use the Tolbert equation. If you want to use the Moody chart, go crazy. Say for F, use equation or chart. Either way, you should get F is about 0.05. And if you use the Moody chart and you get something that's like really, really high, like 1, anything above 1, you're tripping. You're going crazy. On the last exam, I saw a bunch of people doing that. And I was just like, have you ever seen anything that's above 1? Ever? You've done this homework a bunch of times. You ever seen anything like that? Ugh. Anyway, but we want to solve for the total head loss so that we can use our Bernoulli's equation, right? That's why Bernoulli's-esque energy equation thing. Right, so that's why we're doing all this, because we want to find that height h. So, anyway, so we know it's that. So now minor losses. We know our minor losses are it's just h minor is the sum of the k's times v squared over 2g, right? And so total head loss is HF. So our total HF is that, so it should be F times L over D plus KL inlet plus KL exit times V squared over 2G. We just factored all that out. And we're just doing all this symbolically for now. No big deal. So now let's do the head loss equation between the tank and the pipe exit. The tank way up here, and then the pipe exit way up here. So I'll call this like A up here and B down here, right? And don't worry about this figure for now. This will be for figure, so we'll call it figure C for part C. But so for now, we're taking this free surface up here to down there. So it's PA over rho G plus 0. We're calling the velocity 0, right? So whatever, plus 0 plus H. And obviously there's no pump, there's no turbine, there's nothing like that. Equals PB over rho G plus VB squared over 2G plus 0. Again, we're calling that height 0 right there. So plus 0 plus our H total, right? And so we just want to solve for this H right here. And these atmospheres, we can just cancel those out too, right? And so we end up getting H equal to V squared over 2G plus H total. So we get H equal to where you know everything in this equation. We know all the parameters. We know V is 3, G is 9.81. We found all this other stuff. And so just plug in, you get H is equal to about 2.18 meters. Right, that's how high the tank has to be to supply that volume flow rate. Or just the flow rate, whatever. So now, let's see, for part C. So for part C, we're removing the pipe and replacing it with a diffuser, just this big diffuser thing right here, with an error ratio A2 over A3 is equal to 0.5. Section 2 being the tank exit, section 3 being the exit from the diffuser to the air. The water is the same height as found in part 2. And the only only minor loss. Okay, so we're only dealing with minor losses here because there's no like pipe anymore, right? And the volumetric flow rate increased 28% to the case with the pipe. Find the minor loss coefficient of the diffuser, KL diffuser, right? So all right, so we know if the volume flow rate increased 28%, then so did the velocity. The velocity had to increase 28%, right? So we'll say V2 equals 1.28 times V, right? Where V equals 3. Equals 3.84%. Meters per second, percent, what am I talking about? So again, we can use just the Bernoulli's equation again, the head loss equation, where there's the only H total, again, we can literally do the exact same thing. We can do the exact same sort of thing we did up here, except H total is now just the minor losses, right? So we can say, PA over rho G plus 0 plus H equals PB over rho G plus V3 squared over 2G plus 0 plus H total, right? Where that's gone, that's gone. Right, and H total is now just equals KL D, which is what we're solving for, times V2 squared over 2G, and H, we already found H. So we can go, this is just 2.18 over here, we already found that. We can say equals times, we want that error ratio because that's how we get that other velocity, that V3 in there. Right, so let's put everything in. You know everything else. We know that V2 is 3.84, right? V2 is 3.84. Plot everything else, and we know the area ratio, let's see, A2 over A3 said was 0.5. We can plug that in, do all that. We get KL, solve for KL, is 2.65. Just do some algebra for it. Follow the key. That was kind of a quick explanation. Just go back, follow the key. Yeah, just solving for a minor loss coefficient. All the base equations. Just go do some algebra, plug in all the numbers you're given, do all that sort of stuff. Do your head loss equations. Pretty chill. Now the last one is going to be a friction drag one. It's pretty easy. So we've got a flat plate that's mounted in a wind of velocity u infinity, and the boundary layer, so the boundary layer is tripped at the leading edge such that it's fully turbulent, right? We've got some little, usually in the lab I work in, we just put like a little, you just put some sort of little surface roughness thing right there, and it just trips up the flow and makes it all turbulent so that you don't have a mixed boundary layer. So for this first part, everything's all turbulent. We're using all of our turbulent equations. We also have a small skin friction sensor right here, is that x equals 2 and reads tau wall is equal to 2 pascals. And the plate is 50 centimeters wide, 5 meters long. So for A, we want A, find u infinity, which is the wind velocity, right? So we know the boundary layer is fully turbulent, so we're going to use all of our turbulent equations. And on an exam, they'd probably give you all these equations, so whatever. We know tau wall is equal to, tau wall over 1/2 rho u infinity squared is equal to the skin friction coefficient, right? Which we also know for a turbulent boundary layer is just 0.0576 over the Reynolds number at whatever location you're at, REX, to the 1/5. And you might see slightly different equations for this. That's fine. Everything is empirical for turbulent boundary layers. It's not that big of a deal. So we know tau wall. We want to solve for u infinity. We also know the Reynolds number is equal to rho u infinity times L, or I guess in this case it's x. All right, that is x over mu, right? And I guess, does it say? It doesn't even say. Okay, we're using rho equals 1.2 kilograms per cubic meter, and viscosity equals 1.81 times 10 to the negative 5 Pascal seconds, right? So solve for u infinity. All right. So we get u infinity equals, in brackets, 2 tau wall over density times density times x, which is 2, over viscosity to the 1/5 times 1 over 0.0576, and all of that to the 5/9 power. Right, this is just from algebraing all of this stuff out. Just do a bunch of algebra. If you want to just go up and find the, I guess you can't find the Reynolds number straight up, but yeah, just sub everything in, plug it in your calculator if you've got a calculator with you. You get u infinity equals 35.3 meters per second. Cool. So for now, for part B, estimate the boundary layer thickness delta at the downstream edge of the plate. Well, cool. We know the free stream velocity already, and we know there's just a nice equation straight up for this. And so the one form they'll probably give you will be something like this, where it's the ratio, it's the boundary layer thickness ratio to the length of the plate. So it'll be like delta over x equals 0.371 over REX to the 1/5 power, right? And we already know from above, we already found that the velocity is 35.3. So we can say REX, where the x in this case, since we're taking it at the far edge, it'll be the full length of the plate. So be rho u infinity L over mu. And we know L is 5. We know we just found free stream velocity, and we're given these two things. So REX is 1.18 times 10 to the 8, which is turbulent anyway. So cool. So now we know this. We know x, again, is 5. Plug in, just do the math for this. We just found REX, take it to the 1/5 power, do the math for it. We get delta, should be about 71.5 millimeters. Right, after doing all that math. So that boundary layer thickness as it develops as you go along here, it's 71.5 millimeters right there. Cool. So now for part C, it says, part C says, should the trip be removed and the boundary layer is allowed to transition naturally to turbulence, what will the skin friction drag force be on the plate? Consider only top surge for the wetted area, AW, and ignore the influence of plate thickness and mounts. Yeah, obviously. So since we're removing the trip, and we already said that the boundary layer, the Reynolds number for the full thing is 1.18 times 10 to the 8. So it's going to be mixed, right? So it's a mixed boundary layer. So we know that our CD, right, for a mixed boundary layer, our drag coefficient is 0.455 over log RE of the whole length to 2.58 minus 1700 over REL, right? And we know the REL, that's the same one we found up here. It's the full length of it. So it's, 1.18 times 10 to the 8, whatever. Plug everything in, take the log of it, whatever. You get CD is about 0.0021, right? And so now we know that now we can just go and straight up use our other equation where we know CD is also equal to the total drag force times 1/2 rho U infinity squared times the wetted area, AW. In this case, the wetted area is just the area of the plate. So it's equal to 0.5, because 50 centimeters wide, times 5 meters long, equals 2.5 meters squared, right? And so we just want to solve for FD. So we get FD equal 1/2 rho U infinity squared AW times CD. You know everything, plug everything in. Got the total drag is about 3.92 newtons. All right, so that's that. So all of these are very pluggy-chuggy, these kind of equations, all this stuff. You're given a bunch of numbers, go do some math with them, do some algebra, spit out a decent answer. You'll live. Anyway, all right, so that's the review. If you have any questions specifically, shoot me an email, comment on the video, whatever. If you don't have my email, comment and I will give you my email. We can chat things over. But with all that being said, yeah, good luck on your finals. Hope it all goes well. I will be there in one of the sections proctoring, so you'll see me there. All right, have a good one.